All right, in the last class, we had discussed about the transformation between the body and the NED frame using this rotation matrix, and also we looked at how the angular velocity gets transformed. Saw that here, right? The angular velocity between the body fixed frame and the Euler lathes, how does the transformation look like? And we saw that this particular transformation is singular when we have theta equal to plus or minus 90 degrees in this case. All right, then we started to introduce, if I'm not wrong, we talked about the 6 degree of freedom kinematic equations of motion, where the positions and the angles or the orientation in the NED frame can be expressed in terms of some transformation matrix J times the same quantities in the body fixed frame. And that's what we looked at. We also simplified it based on a 3 degree of freedom system, because when we are dealing with ship dynamic positioning, our primary idea will be to look in the horizontal modes of motion, so surge, sway, and yaw, in which case that reduces a little bit, but there's an assumption inbuilt that the roll angle and the pitch angle are small during the normal operation. And then in this case, the rotation matrix simplifies and we can kind of express the quantities as shown here. We started off a little bit about the Quaternions. We discussed some of the relative initial definitions of the Quaternions, but we really didn't get into the depth of it. So we'll start off from here just so that we are in the same page, and we'll continue today with Quaternions. So whatever kinematics we described using Euler angles in the last class, we're going to look at the same kinematics described through Quaternions in this particular class. So before I get started, any questions? No questions?
No, sir.
All right. Okay, so then let's get started. So we talked about this notation of a simple rotation, where we are taking one frame and we are transforming it into another frame by taking a simple rotation about a fixed line, which is called as the axis of rotation. So taken one particular, about that axis, we rotate one frame by a certain angle to reach to the second frame. And that when we perform this rotation, it is important to note that this line L, about which the rotation is being performed, that remains unchanged throughout the motion. So the axis of rotation really doesn't change. It's only that the frame is rotated about that axis of rotation to reach the new orientation of the frame. And we understood that this vectors which can be in one frame can be expressed in the other frame by using this rotation matrix. And we looked at this classical example of linear velocity, or translational velocity. Where the velocity in the NED frame is given by this, and the velocity in the body fixed frame is given by this, and the two are related using a rotation matrix. Now, since we are defining things with respect to the simple rotation, it makes sense to define this rotation matrix, which was purely using Euler angles before. We now want to characterize it in terms of this simple rotation that we introduced. So we want to characterize it in terms of two things. One is lambda and one is beta, where lambda is the axis of rotation and then beta is the angle by which we rotate. So in this particular case, I told you that Euler has shown that the rotation matrix, which is parametrized by lambda and beta, can be expressed as the identity matrix plus sine of beta times the skew symmetric matrix formed by the lambda vector plus 1 minus cosine of beta times the skew symmetric matrix characterized by lambda squared. And the idea here is that every change in orientation of any two frames can be produced by a simple rotation of one frame with respect to the other frame. And that is valid very well in the three-dimensional space or the Euclidean space that we are interested in. So in Euclidean space, this holds true. Okay. Now, we saw that in the rotation matrix, we characterized it using the Euler angles. There was a singularity when our theta was equal to plus or minus pi by 2. And this we were considering for a zyx order of rotation. So now we are going to discuss the alternate representation using the quaternions, which are characterized by 4 parameters: eta, epsilon 1, epsilon 2, and epsilon 3. And you can think of this as eta being the real part and these 3 representing 3 imaginary parts of the quaternion. And a unit quaternion satisfies the condition that Q transpose Q is equal to 1. Notice that what will be this Q transpose Q when I multiply this out? What do I get?
The sum of squares of all the terms, right? The real parts and the imaginary parts.
Correct. So we will get the sum of squares of all the terms. So we'll get eta square plus epsilon 1 square plus epsilon 2 square plus epsilon 3 square. And that should turn out to be 1. Then the quaternion is said to be a unit quaternion. Then last thing we defined last class before we left off was the set Q. So we defined Q as a set of all unit quaternions. So all quaternions which are parameterized by 4 parameters such that Q transpose Q is equal to 1 is known as the set of unit quaternions. So just like we have the set of real numbers, we also have the set of unit quaternions, which will come in handy when we want to talk about representation of orientation using quaternions. Okay, so now we are in a position to derive the kinematics that we looked at last time using the Euler angles, which we will now derive using quaternions. So let's see.
Excuse me, sir.
Yes.
So initially we have to define an axis of rotation for this the process of quaternions to work, right? So for defining that axis of rotation, we need to have a frame of reference, right? So which frame of reference do we use for like we have 2 frames? There is one frame that we'll be transferring to the target frame, orienting to the target frame. So we have 2 frames. So with respect to which frame will we define the axis of rotation?
So actually it doesn't matter because the axis of rotation is that the orientation of that axis actually doesn't change, right?
Okay. It won't change.
Yeah, I mean the vector which is pointing with respect to that vector in the lambda direction really doesn't undergo a change.
Okay,
The
fine.
plane is undergoing a change with respect to lambda.
Right. Okay, fine. Yeah, I think I got it now. Yeah.
Got it?
Yeah.
Okay. Okay, so now when we try to express this, we already saw this. This will be our starting point in order to look at the rotation matrix. So instead of being characterized with respect to this angle beta and lambda, we want to characterize it with respect to our quaternions. So we want to characterize it in terms of eta, epsilon 1, epsilon 2, and epsilon 3. So note that epsilon 1, epsilon 2, and epsilon 3 are basically a scaled version of that lambda vector in the sense that it is lambda multiplied by sine of beta by 2. whereas eta itself is cosine of beta by 2. That representation yields us that when I take a square of each of these parameters and add them up, I'll get the value 1. Is everybody with me?
Yes, yes.
Okay, everybody?
Yes, sir.
All right. Okay. So notice here that lambda represents the unit vector. So therefore I can find, if I knew epsilon, I can find lambda by simply normalizing it. So what I'm doing, I'm taking the vector, dividing by its norm, and as long as that norm is not equal to 0, I can find what is that unit vector about which the rotation is happening. All right. So if I want to characterize that quaternion in terms of lambda and beta, this is how it would look. I'll have cosine of beta by 2, lambda 1 times sine of beta by 2, lambda 2 times sine of beta by 2, lambda 3 times sine of beta by 2. And then, as I said, the norm will be given by 1. Before we proceed on, there is another thing which I want to introduce, a product of quaternions. So we define the product between two quaternions using this operator here. Okay, so it is characterized by a circle with a cross in it. And this will be important because when we try to look at what is happening to the angular velocity transformation in terms of quaternions, this product will come in handy. So bear with me as to why this product is like this. Just bear with me and take it that it is defined in this manner. So if I have Q1 and Q2 quaternions, where Q1 is given by eta Q1, epsilon Q1, and so let me call that as a vector. Okay, and then Q2 quaternion, which is nothing but eta Q2 and epsilon Q2 transpose. Then this product between two quaternions, Q1 and Q2, is defined as eta Q1 times eta Q2 minus epsilon Q1 transpose times epsilon Q2. Okay, so notice that this value here is scalar. Correct? Everybody with me?
Yes, sir. Yeah.
Okay, because this thing is 3 cross 1 and this is 1 cross 3. So when I multiply, I'll get a scalar value. So that will be the first value of the product of the quaternions. Now, the next components, which is the other three components of the quaternion, are defined as eta Q1 times epsilon Q2 plus eta Q2 times epsilon Q1 plus the skew symmetric matrix obtained by epsilon Q1 times epsilon Q2. So notice that this here is a 3 cross 3 matrix multiplied by a 3 cross 1 vector, so this will be a 3 cross 1 vector. Similarly, this also will be a 3 cross 1 vector. This also will be a 3 cross 1 vector. So when I put everything together, this product of the two quaternions will also be a 4 cross 1 vector, which a quaternion should be. Is that making sense?
Yes, sir.
All right. Now, notice that when we are performing this operation, I take a product between Q1 and Q2 that is not the same as taking the product between Q2 and Q1. And where is the problem coming?
The skew symmetric matrix.
Correct. The term this one is why that product cannot be the same. Okay, that is the reason why these two products will not be the same. So notice that this product of quaternions is not commutative. which means the order in which I take that product really makes a difference on what is the final answer. However, the sum of two quaternions is commutative. Q1 plus Q2 is equal to Q2 plus Q1. So addition is commutative, whereas product is not commutative. So that is the main property that you need to remember. And you also need to remember that the product of the two quaternions is actually denoted like this. Okay, so when I am going from the B frame to the N frame, I want to find out what is my rotation matrix in terms of the quaternion. And I want to find this in terms of the quaternion, which means that this expression, which is written in terms of lambda and beta, I want to transform that in terms of the quaternion. How do I go about doing that? I'll break apart this sine beta as 2 times sine of beta by 2 times cosine of beta by 2. And 1 minus cos beta can be written as, what can it be written as?
Sine square beta by.
Sine square beta.
Correct. Once I write it in that manner, it is easy to see that if I take this sine beta and multiply it into this matrix, instead of the skew symmetric matrix of lambda times sine of beta by 2, what I am essentially having is a skew symmetric matrix defined in terms of epsilon. Is everybody following me? Because epsilon is nothing but sine beta by 2 times lambda. Everybody with me on this?
Yes, sir.
All right. Similarly, when I have sine square beta times s of lambda to square, I can actually convert that into s of epsilon. Now, what is left here as cosine of beta by 2, we know that that is nothing but eta. So, if I want to express this rotation matrix in terms of the quaternion, it simply is the identity matrix plus 2 times eta times the skew symmetric matrix with respect to epsilon plus 2 times the skew symmetric matrix due to epsilon squared. Is this making sense for everybody?
Yes, sir.
All right. Now that we know how to parameterize the rotation matrix, we know that the linear velocity transformation or the translational velocity transformation simply becomes that the position vector of the origin of B with respect to n, the time derivative of that is nothing but the rotation matrix times the velocity expressed in the body fixed frame. Now, only thing here is that this rotation matrix, which was previously characterized using the Euler angles, we are now going to express that with respect to the quaternions. And by using this above expression, which we have here, we can expand these terms out and we can see that that rotation matrix comes out to be 1 minus 2 times epsilon 2 square plus epsilon 3 square, so on and so forth. You see that this is the terms which you get out. Is that making sense?
Yes, sir.
Okay. You can clearly see here that this 1 is coming from the identity matrix. And then whatever terms which are there with eta, that is coming from that skew symmetric matrix times eta, which is this term here. And then finally you have the cross product terms, the squares terms. Those are coming from the s of omega, s of epsilon squared term. That is where that term is coming from. So what we saw as the rotation matrix being specified in terms of the Euler angles before, we are now seeing the same rotation matrix specified in terms of the Quaternion. The rotation matrix continues to have the same properties in the sense that whether it is defined with respect to Euler angles or whether it is defined with respect to Quaternions does not matter. Its inverse must be equal to its transform. Now, the more interesting aspect which one needs to discuss is the angular velocities transformation. So, remember that we defined this, we talked about this in one of the previous classes, that if I take a derivative of the rotation matrix, I get actually the rotation matrix times the skew symmetric matrix with respect to omega. Does everybody recall this?
Yes, sir.
Everyone?
Yes, sir.
We
Yes,
talked
sir.
about the idea that there will be 9 differential equations characterizing the derivative of a rotation matrix. Now, what we will do is, into this rotation matrix, we will substitute our quaternion. So I'll substitute our expression in terms of the quaternion into this differential equation. Okay? And then I will try to simplify it a little bit. I'm avoiding a lot of math here. So in essence, what I get out of it is the derivative of the quaternion can now be expressed as some quantity here, which depends on the quaternion itself, taken as a cross product, or taken as a product of this quaternion times the another quaternion whose components are 0 and body fixed angular velocity. Okay, the idea is that we use this expression and we substitute r beta n, rbn, in terms of the quaternion. Okay, once we do that, we can do the manipulation to find out the expression for what is the 4 governing differential equations for how the quaternion is actually changing over time, especially when the body has an angular velocity involved with it. Is this making sense? I'm not telling you how it has come. I'm telling you the basic process behind it. We are using that rotation matrix to substitute it and then get to this. But please understand the idea that we are using that methodology with a lot of linear algebra simplifications to get to the point where we are saying that now the differential of the quaternion can be expressed as some quantity, which is half times the product of the quaternion with the angular velocity.
Okay, sir.
Okay, I leave it as an exercise for you to see if you can actually derive it. It's not very straightforward. There's a lot of mathematics and a little bit of linear algebra that you have to apply. But if you're really interested, you can try it out and see. One other aspect to check it might be that you might take a quaternion, an arbitrary quaternion you define, and then formulate the rotation matrix with respect to that and see whether the rotation rates which you are getting from the above differential equation, you can use that to find out what the quaternion's rates look like. Okay.
Okay, sir.
So if I time step it by, let's say, a small delta t, which means that, let's say, I know the rotation matrix b to n at a particular time, and I know what the angular velocity of the body is. Okay. Okay. Then I can find out what the rotation rate is, how the rotation matrix changes over time. So I can use this expression to calculate the RBN at a new time step. Yes?
Yes, sir.
Is that making sense for everybody? If it's not, please tell me. See, I know RBN dot is equal to RBN times the skew symmetric matrix obtained by omega NB. Okay, so if I know the quaternion at some time, let's say some time t, okay, and I also know the angular velocity of the body at that time t. So these two are known. Okay, from this I can calculate what will be my rotation matrix at time t. Okay, using these two pieces of information, I can compute my rotation matrix at time t plus 1. Is that making sense?
Yes, sir.
Okay, this is nothing but the rotation matrix at time t plus delta t times RB.
RB dot.
Yeah, a simple Euler scheme, right? So I now know what is the rotation matrix at time t plus 1. The other way to verify the above formulation would be that I can take this value of q and I can take this value of omega and use that to find out qbn dot, correct? Using this expression which I have shown here,
Yes, sir.
right? So that I'm having this as 1/2 of qbn taken a quaternion product with 0 and omega nb. So I now know this fellow at time t. I know it. Using that, I can find out the quaternion at time t plus 1, delta t. Which will be quaternion at time t plus delta t times quaternion rate at time t. Right? Once I have the new quaternion, I can also formulate using this fellow the rotation matrix. What I get from here should match with what I got from here. These two must be equal.
Yes, sir.
So in a way, what we will do is I'll set up a question for this on MATLAB Grader, and that will allow us to see this in action. So let me do that and put it up on MATLAB Grader. That way you get to see that the quaternion product which you're doing is actually nothing but the rotation matrix change. Okay, we will get to see this in the assignment. It's a good way to go forward on it. All right, any questions so far? So far, okay, everything?
Yes, sir. Yes, sir.
Yes, sir.
I'm not hearing a unanimous yes. Is there some cause for confusion? Now is the time to ask. No hesitations. Anything which is not clear.
It's fine, sir.
It's maybe like it's just that the derivation we are not actually doing. So just seeing the result. And, like,
Correct. The result is springing up on you. We are not actually seeing it. So what we will do is we'll set this up in the assignment.
yes.
Okay. So as to convince ourselves, we'll put it up as into that. Okay. We'll do that and then we'll satisfy ourselves. Okay. Now, this Quaternion derivative, which we are now showing to be as the product of the Quaternion itself times the angular velocity, can also be expressed in a matrix format where we have 1/2 minus epsilon transpose eta times I plus S of epsilon. Let's see how this came through. Okay, we'll try to see how this particular thing has come through. What I want to express this as is some matrix times the angular velocity of the body. That is what I want to express that as. So if I go back to my expression for the product of the quaternions, and then we start seeing from there, it will be clear. What is eta q2 here when I'm taking with respect to this?
0.
It will be 0, right? So this term is not there. And then I only have this term and this term. Let's actually derive it so that it's simple and straightforward. It's not that hard. So let's do that. Okay, so we are looking at Quaternion cross product 1/2 of that times 0 and omega NB. And we know that Quaternion product is given by eta q1 eta q2 minus epsilon q1 transpose times epsilon q2. I hope I'm putting the formula right. We see that. Correct. And then eta q1 times epsilon 2. All right. And then the next one is eta q1 times epsilon q2 plus eta q2 times epsilon q1 plus skew symmetric matrix due to epsilon q1 times epsilon q2. This is what we have as the product. Now, notice here that in this above product where we are taking, what is our epsilon q2?
Omega NB.
Is omega NB, right? Is the body fixed angular velocity of the body in the body fixed frame. And eta q2 is 0, right? All right. And now I'll denote eta q1 as eta and epsilon q1 as simply epsilon. Okay? Assuming that our q and b is given by eta epsilon transpose. Does that make sense? Yes, so far?
Yes, sir.
So we simply now plug in these 4 values into our set here, and that will do our trick. So what do we get? Eta 1 and eta q2 is 0. So this term goes away. So then what we are left with is minus epsilon q1, which is nothing but epsilon. So minus epsilon transpose times omega NB b. And what we are left with below here is eta q1 is eta times epsilon q2. that is nothing but omega NB B. Eta Q2 is 0, so this term is 0. And now we have the skew symmetric matrix constructed with respect to eta Q1. So skew symmetric matrix with epsilon times omega NB. Now I want to express this as some matrix times omega NB. So I know what to do about it, nothing but minus epsilon transpose, and I have eta times the identity matrix plus the skew symmetric matrix due to epsilon. This matrix multiplied by omega NBB will be giving 1/2 of it, that is 1/2 missing all throughout because of that 1/2 factor. And this is nothing but our rate of change of the quaternion. Yes?
Yes.
Why are we doing this? We want an equivalent to what we saw before. Remember when we had the Euler angles, we wanted to see how the rate of change of the Euler angles relates to a matrix T, okay, which depends on the Euler angles itself, times the body fixed velocity. Oops. Where did it go? Yeah. This is what we saw before. Where is my pointer? Sorry. Yeah. This is what we saw with the Euler angles, correct? When we were looking at the angular velocities transformation, we want an equivalent for that with respect to the quaternion. So we want to see how the quaternion's rate of change is related to the body fixed velocity and the angular velocity of the body in the body fixed frame. And this is that matrix which is relating it. What is the size of this matrix? What should be the size of this matrix?
It should be 4/4. No, 3/4. 4/3, sir. Yeah, 3 columns and 4 rows.
Yes. Because we have the quaternion which is 4 cross 1 and we have the angular velocity of the body which is 3 cross 1. So this thing should be 4 cross 3. Okay, it should have 4 rows and 3 columns. Let us see if we expand this fellow out, what do we get? Yeah, so if I expand this fellow out, the first row is minus epsilon 1 minus epsilon 2 minus epsilon 3. Right. Next one, I have the identity matrix plus the skew symmetric matrix with respect to epsilon. So I have eta, eta, eta minus epsilon 3, epsilon 2 minus epsilon 1, epsilon 1 minus epsilon 2, epsilon 3. This times 1/2. That is my so-called P matrix, which depends on the quaternion to Bn. Is that making sense?
Yes.
Yes.
That is what we see here. Our T matrix, which relates our body fixed angular velocity of the body in the body fixed frame to the rate of change of the quaternions, can be related by this T matrix which is now given by these components which we just saw. It can be shown that if I take this T matrix and multiply it by its transpose, I'll get 1/4 of the identity matrix. Okay, and this identity matrix will be a 3 cross 3 matrix. Sorry, this should be in 4 cross 4 matrix. There's a mistake here. This should be I4. Okay, because T will be 4 cross 3 and T transpose will be 3 cross 4. So the resultant matrix should be 4 cross 4. Okay, all right. So what we have seen is that when we have the quaternions included, our linear velocity, the position of the body fixed frame's origin in the NED frame, can be represented still as a rotation matrix, but now that rotation matrix depends on the quaternion times the velocity of the body in the body fixed frame. Okay, and we saw what the expression for this looks like, right? 1 minus 2 times epsilon 2 square plus epsilon 3 square, and then so on and so forth. You had all those terms. Okay, it's purely parameterized in terms of the quaternion. We also looked at the idea that the rate of change of the quaternions with time can be related as the T matrix, which again depends on the quaternion, times the angular velocity of the body in the body fixed frame. Notice, however, here that this is a 4 cross 3 matrix in order to be consistent. Okay, so in the previous case, we had the Euler angle rates related by a T matrix, and we saw that that thing relates to the angular velocity of the body, and this matrix was becoming singular when theta was equal to plus or minus pi by 2. Everybody remember that?
Yes, sir.
Now, however, when we are looking at the Quaternion representation, this is our T matrix, and you can see that there is no such singularity where this matrix rushes off to infinity. Yes?
Yeah.
So therefore, this matrix is not singular, and we have now come up with a representation of the orientation in terms of quaternions, which is non-singular. So we can use this representation, but the only downside is I have one extra parameter to parameterize. So instead of getting away with 3 parameters, I now have to use 4 parameters and then define my orientation. Is that making sense? At least where the difference is coming between the case where we are using the Euler angles versus where we are using the quaternions. The difference comes in this T matrix.
Yes, sir.
Making sense for everybody?
Yes, sir.
Why the feeble yeses today? Something is not making sense? Tell me frankly, what's the problem? What's the issue? No issue?
I think it's fine, sir. Okay. Thanks.
Okay, all right. Okay, all right. Now that we have defined the quaternions and how the rates of the change of quaternion relate back to the angular velocity of the body, and how the translational velocity can be expressed in the NED frame with respect to a rotation matrix which is now parameterized by the quaternion, we are now in a position to describe the 6 degrees of freedom kinematic equations where we are using quaternions instead of the Euler angles. So when we are looking at the 6 degree of freedom system, the generalized position vector which we saw before had x, y, z, so those parts are still the same. And instead of the 3 Euler angles, we now have the 4 parameters from the quaternion coming into the eta vector. Okay. The angular velocity is the same, so this is the same as before. And now we want to relate eta dot, the generalized positions derivative of that with respect to time, or we call these as generalized velocities. All these as a generalized position. So the generalized velocities can be related to the velocities in the body fixed frame using this transformation matrix. Notice here that we have this T of QB. Okay, so this is slightly different than what we had before, which was the transformation with respect to the Euler angles NB. That was a 3 cross 3 matrix, whereas this will be a 4 cross 3 matrix. So when I take the total transformation, what will be the size of this big matrix which we see here?
7 cross.
That will
7
be
cross
7
6.
cross 6, right? Because there are 6 quantities here, 7 quantities here, so the total should be 7 cross 6. Where our eta vector, the generalized position vector, belongs to a space of 3 real numbers denoting the position and a quantity from the Q set, which is denoting a unit quaternion, and V here represents 6 real numbers, and the J matrix is F size 7 cross 6. Okay, this sounds very well and good on theory, but you have to see it in action to really appreciate what is going on. And I'm hoping that we will put up an assignment in the coming week where you can kind of take a look at what is the implementation differences between them. For one thing, since we are dealing with unit quaternions, it makes sense that whenever we are doing the implementation, we must verify that the norm of the quaternion actually doesn't change. Because when we are integrating cube dot bn to get the new value of the qn, so we saw that before, we were trying to get the quaternion at time step t plus delta t as the quaternion at time step t plus delta t times q dot bn, right? But we have to ensure that every time we get a new quaternion, it is still a unit quaternion. Which means that when I'm implementing, I will compute the value of the quaternion at time step 0, and I'll step it forward in time where I get the value of the quaternion at time k plus 1 using the value of the quaternion at time k, and where I'm using this expression to denote q dot bn that we just derived, and I'm Euler time stepping it by a delta t equal to h. So in this case, my delta t is equal to h. I have to follow this step by a normalization step. So this step 3 is called a normalization step. Where I take this unit, the quaternion that I obtain, and I normalize it. I make sure that its norm is equal to 1. And how do I do it? I simply divide it by the square root of the norm, and that does the trick for me. All right, is that clear till now? Any questions so far?
No questions.
All right. Okay. Now, we also need to understand how to convert a unit quaternion into a Euler angle and how to convert an Euler angle into a unit quaternion. It can be actually shown that if I have Euler angles defined as phi, theta, and psi, and the order of rotation being z, y, and x, then the quaternion corresponding to that orientation is given by this expression here. So we are simply saying that I'm taking the quaternion for the corresponding three Euler angles, and it can be shown to be this big matrix here. So if I know the Euler angles phi, theta, and psi, I can plug them into here to get what is my value of the quaternion. Similarly, if I want to get the Euler angle from the unit quaternion, that too can be done fairly easily. That I find out what is the value of phi, theta, and psi in terms of the parameters of the Euler, in terms of the quaternion's parameters. And this is what you will get. Notice here that we are using a tan 2, and that is very important. That is not similar to using a tan in MATLAB. A tan takes a single argument, whereas a tan 2 takes two arguments. The reason why we want to use a tan 2 is because its range is from minus pi to pi. Whereas a tan only gives me the angle from minus pi by 2 to pi by 2. So which means it's not unique representation. So in order to be having a unique representation of the angle, we must always ensure that we are using a tan 2. Notice here that when we are close to theta equal to plus or minus pi by 2, we need to be careful because the Euler angles may not hold up properly. Okay, so this is how we will convert from the Euler angles to the unit quaternion, and this is how we will convert from the unit quaternion to the Euler angles. Is that making sense?
Yes.
Okay. All that is doing actually, if you look at it very carefully, what you're doing in essence here is formulating the rotation matrix. Okay, so you are taking these angles, formulating the rotation matrix, and then seeing the rotation matrix due to this fellow, and then comparing the two to observe how you can actually compare the two terms. These two will be equal, right? And that will give you these expressions for these different values of the quaternions from the Euler angles. The same process applies for the other way around also. You look at the rotation matrix and see which are the terms which are giving you phi, theta, and psi. That is where you will get. So just to take it as an example, let us go back and find our angle phi, for example. Okay, so from the rotation matrix. Okay, so this was our rotation matrix, isn't it? So if I wanted to find the angle phi, how can I find it? Yes.
So the ratio of these last rows, two terms.
These two guys, right?
Bottom two, yeah.
Correct. So I can take c theta sine phi and cos theta cos phi. And when I plug them into the a tan 2, I should get my value of phi. right? So I need the terms which are R33, right, and R32. R32 by R33, tan inverse of that is giving me 5. Now, if we go back to the rotation matrix and see what these two terms are when they were parametrized with respect to the Quaternion, which we saw today, it will be the ratio of these two terms, isn't it? Yes?
Yeah.
Because this term is R33 and this term is R32. So if we look at what the value is here, this value is nothing but R32 and this value is nothing but R33. Okay, so that is how we look back at the rotation matrix and identify what is the relationship between the quaternions and the Euler angles. Okay, so that completes our basic understanding of what the Euler angles and the quaternions are doing. So we have looked at two different ways how the orientation can be expressed. One in terms of the Euler angles, where there is a singularity when we are looking at some particular angles, whereas the quaternions don't have that singular problem, and then where you need to express it in one extra parameter. You start to have an extra parameter that you need to account for your kinematics. Okay, everybody clear so far?
Yes, sir.
Yes.
Yeah.
Okay, so next class we will start discussing about how to transform between the Earth-centered frames and the NED frame, which means that given a latitude and a longitude, how do I transform that into a flat space as to where the position of my vehicle is? So how to convert a latitude and a longitude pair in order to understand what I am getting from it. That is what we'll discuss tomorrow. Okay. All right. So that's all for today. Let me stop recording.